Good morning, everyone. Welcome to today's webinar, What Have Monads Ever Done for Us? I'm thrilled to have Dick Wall presenting today. My name is Laura Masterson. I'm the Community Manager here at TypeSafe, and I will be moderating today's presentation. Before I hand things over to Dick, I just wanted to go over a few things. First of all, the call is going to be recorded, and it will be available for replay soon. Also, if you have questions throughout the presentation, there's a little chat box in the lower left-hand side of your screen. You can just submit your questions or concerns there, and I will respond to those as we go. If it's a technical question for Dick, we'll save some time at the end for a Q&A. All right, with all of that, I'm going to hand the floor over to Dick and let him take it from here. Dick, thanks for joining us today.
Okay, thank you, Laura. Good morning, everybody, or good afternoon, wherever it is you are. Thanks for joining us. This is quite a overwhelming response. Obviously, an interesting topic, so I will do my best to live up to expectations. So I did this talk first at Devox UK, and I know the crowd there. A lot of people have, or at least familiar with Monty Python's Life of Brian, and there's a scene in that where some rather upset or irritated folks are sitting around saying, what have the Romans ever done for us? And the answer comes in as, well, there's sanitation, medicine, education, wine, public order, irrigation, roads, the freshwater system, public health. Apart from that, what have the Romans ever done for us? And someone says, brought peace. And basically the idea here is that these things called monads that there's a lot of fuss about, particularly since functional languages started picking up in popularity again recently. There's a lot of confusion about them. There's a lot of tricky topics or ideas around them. And a lot of people are like, well, why should I even bother to learn this? And truth is, you don't really need to know them to use them. But the chances are you are using them for a lot of these kind of things. Not quite sanitation, roads, and public health, but definitely, being able to use futures effectively, or options, or collections. There's a lot going on behind the scenes in those that are using these concepts like monoids, functors, and monads. And if you understand them, you're able to harness them and write them and use them for yourself. So that's really kind of what this is, what this talk is about. One of the things I do like to mention is I've been programming quite a long time now, a bit longer than I like to think about. And during the course of all that time, there's been numerous silver bullets that have been thrown up. This is the answer to every problem you have. And just like every other silver bullet, monads are not that. They are extremely useful, just like many of these other concepts are. But, they are useful in specific cases. And people who say, oh, you should use monads for everything, probably are missing some obvious, simpler solutions to many of those kind of things. Okay, so let's start with some of these terms, and in a way that will hopefully make them, clear and non-threatening. And in particular, one of the things that's really nice about this talk, one of the reasons I put it together is, up until now, because of the lack of lambdas in Java, there wasn't really a good way to talk about some of these concepts in a language that most people have used, like Java. And with Java 8 coming along with lambdas, suddenly you can present these kind of ideas and code examples using Java, and it's tremendously liberating. It means there's a bridge for learning that wasn't there before. But we're going to start with something pretty simple, and as of right now, this is not going to use lambdas for the first part of this. We're going to move into those in a little bit. But we're going to start with all of these terms like functors and monads and monoids come from mathematics in particular. Most of them come from something called category theory, which is pretty kind of nebulous and broad and very, very general. But there's a nice simple one that pretty much everybody gets straight away, which is this concept called a monoid. And what a monoid is in mathematics is it's a combination, and it's a perfect example, like a microcosm of what a monad is. A monoid has two specific things and then some rules that govern how it can be used. And the two specific things is it needs a value that you start from. This is sometimes called 0, although it's not always 0. It's a starting value. It's sometimes called identity. And basically, that thing plus a combiner or a combination operation form a monoid. An example of this is something like plus. Plus and 0 together make a monoid. So if you take any number and you add 0 to it, you end up with that same number. If you take 0 and add any number to it, you end up with that number. And if you add two numbers together, you get the sum of those two numbers. And that's, between them, that is a monoid. The same thing for multiplication. Your start value would be 1, and the operator would be multiply. Multiply anything by 1, and you get that item. So those are the two operations. There's a starting value, 0, or start, or identity, whatever you want to call it, and the operation to combine them. Similarly for strings here. Oh, I've got to turn on my little arrow. For strings, if you start with an empty string and you combine a string with that, you end up with the same string, and so on. Those are the monoid operations, or the monoid facets, if you like. And the rules are, for a monoid, no matter what order you apply the combiner operation, whether you do, if you have like 3 plus 4 plus 5, or 4 plus 5, and then you add 3 to that at the beginning, you should end up with the same value. That's one of the monoid laws. The other one is that if you take any item and add the identity, or not add the identity, combine it with the identity, you should end up with the same item. So, bringing those together, that is what makes a monoid. You've got the 0, the combiner, and these laws that govern how they can be used together. Okay, now before we go further, I'm curious to see, first poll of the day, who here has actually used Java 8 lambdas in some kind of capacity? I think here, I haven't done this before, but you're supposed to click on the yes or the no if you use them. And this is just to give me an idea of how much. Oh, yeah, they're coming in. These are coming in, so I'll give it a second. I see actually the majority of you have not, so I will take my time explaining lambdas a little bit when we get to that point. Now how do I'll close the poll. So, yeah. All right, that's good, thank you. Oh, maybe I should let everybody see the results of those. So as you can see, there are quite a few people who have used lambdas already. I wonder how many people, and what we should have asked is how many people are here because they want to know more about lambdas rather than monads. But I guess I'll just assume you guys are interested in them anyway. So, okay, so let's take a look at a monoid. Now, we're not going to be using lambda for this. This is just a simple, plain old interface in Java that anyone can implement. So if we wanted to create our own monoid, this is the kind of technical aspects of what you need to provide, and then the rules are just something you have to follow. Those are a bit more abstract than just filling in an interface. You actually need to make sure that if you add A and B and then C, that's the same as adding A to the result of adding B and C together, or combining them. But the actual interface in Java would look like this. For any monoid over a generic type, this could be an integer or a string or whatever, you need to provide a start, which gives you back that 0 value, or that starting value, and then you need to provide a combine. The names don't matter. What really matter here are the type signatures. So the combiner takes an A of type T and a B of type T and gives you back some combination of those as a type T. Okay, and it's a very simple interface to understand. Now if we want to have a look at how you can implement some of those, let's have a look at the two integer ones that we just showed. Incidentally, I kind of glossed over that bit, but minus and divide are not monoids. They can be defined in terms of this interface, but they violate the monoid laws, in particular the associativity. You can see this by just taking three numbers. If you say 5 minus 3 minus 2, you end up with 0. But if you take 5 and then you take off the result of 3 minus 2, you end up with 4. So you don't get the same answer. So that breaks that law of monoids, and the same is true for divide. But we can provide ones for integer addition and integer multiplication. They would look like this. So here's an integer add monoid. It's a monoid over integer. It provides a start value of 0, and it provides a combiner which just takes integer A, integer B, and adds them together to give you back that integer. Very simple. Likewise, the multiplication monoid looks very similar, except the starting value now is 1, and the int values are just multiplied together. Now using those, to actually use them, we would want to, now that we know this kind of something about the nature of this type, that it has a monoid defined on it, we can now define a function in terms of that. So now we can say, okay, I've got a list of these items of type T, and I have a monoid defined for this type T that I can use to combine these together. And then I can write a very simple function which just says if the items is empty, we're going to give back the safe value that we know about. We're going to give back that start value, whatever it is. Otherwise, we get the first item, that's X if you like, and then for the rest of the items in there, we combine using that monoid combine function X with the results of the next item, basically. Just keep folding those items over and return the value. This is a very naive one. The reason monoids are important, as I say, this is a very naive implementation that just runs through them in order. But the advantage with sorry, I just saw a question which distracted me very briefly, but I'll get to that in a second. The nice thing about monoids is when you have a monoid defined that follows the rules, you can actually split up the problem and parallelize it, across multiple cores. You can take parts of these, feed them off to different cores or different processes, and then combine them all at the end. So that's kind of the advantage of using a monoid, is you get this built-in ability to parallelize the problem. So the question here from Satendra Tiwari is string a monoid? String itself is not a monoid, but string concatenation can be. The string concatenation monoid would be an empty string and then concatenating two strings together, A concatenated with B. And so that satisfies all of the requirements. If you add an empty string, or if you concatenate an empty string to the beginning or end of an existing string, you just get that string back. And if you concatenate strings, no matter what order you evaluate that concatenation in, you end up with the same result. So hopefully that answers that. Okay, in use, just to show this works, we can create a list of numbers, 1 to 10, and then we can apply the monoid to that list. We can do the addition monoid and the multiplication monoid. And if we want to do strings, which is what I just talked about, here's the concatenation monoid, empty string, and then the combiner is A plus B. In this case, plus is string concatenation in Java. And that's the implementation. So it says there's a monoid in Scala Z library. Does somebody use it in production? No, in Scala Z library, monoids are very heavily used. And is every monad a monoid? That's a very deep question. I'm going to come back to that at the end, I think. Just remind me. Okay. So strings combined, here's an example of using the string concatenation monoid. Okay. Up next, we're going to look at functors. That was a whirlwind coverage of monoids. Functors are no harder to understand. In fact, if you've used any kind of collection where you transform the collection, you've already used a functor. So a functor is, roughly speaking, a transformer. It is particularly defined by a function often called map or fmap that is basically an application of a function that you give it over the contents of that collection. And what it does is it gives you back the same kind of collection. If you start with a list, you end up with a list. If you start with a vector or a array, you end up with those types. But the contents can change both in terms of the values and in terms of the type that's in them. So if you have a function that takes an int and turns it into a string, and you apply that to a list, you end up with a list of string rather than a list of int at the end of it. What you really care about in terms of functors is that there's a map method that takes a function and returns a new thing of that same kind that has these transformed contents in it. And we'll see an example. I'm actually going to show you how to write a very naive implementation of that in Java. I should point out that all of these are good exercises to do in Java 8. When you by all means write them and learn to use these concepts by yourself. But when it comes to using them in production, I suggest you throw away your own implementations and use the ones that have been provided by library writers that have been well tested and have all the corner cases and kinks worked out. But it's a really good exercise to write some of these and figure out how to do them. Okay, so let's have a look at a linked list implementation. This is a very simple one using Java 8. I'm going to avoid all of the noise, things like wildcards and things like that, they make it more useful, but they also make it a lot more noisy. So we're just going to look at simple types. And here's an example. I called it dead simple list to give you an idea that it really is about as simple as you can make this thing. This is a top-level abstract class, or abstract type, which is genericized over type T. And then, so we have our dead simple list of type T. This has no implementation. This is just the type signatures for the methods involved. And as you'll see, and I need to turn my little green thing on again. Right here is this map function. This is the thing that makes it into a functor. And so the map function here returns, given another type of u, which could be the same. We could go from an int to an int, but we could also go from an int to a string or an int to a person or any other kind of transformation that we want. Given another generic type, our map takes a function. This is a Java lambda, a function from T to U. So it takes in a type T, which is our type, and gives out a U, which is the new generic type. And what it will do, we haven't implemented it yet, but when we write the implementation, it will map that function over each item inside the list, construct a new list with the results of that, and return it. And that will result in a dead simple list of type U. And then we've got just a couple of other things that help us with the demonstration here. These don't make it a functor. These are just very convenient for the implementation. One of them is a Boolean that says whether this is empty or not. And the other one just gives us back the contents as a string so that we can actually look at what we've got as a result of running that. Okay, so let's take a look at two of these implementations. And at this point, this is a good opportunity to introduce another concept that you see a lot when using things like monoids and functors and monads. And this is called an algebraic data type. And what that is you just saw part of it. It's a type at the top level, usually abstract, that there are a finite, usually fairly small number of subtypes of, concrete implementations of. An example of this kind of thing we'll see in a minute is the optional type in Java. So there's an optional, and basically optional has either something in it or nothing in it. So there's two concrete possibilities. There's a none and a some, or a nothing and a full. The names kind of vary depending on the implementation. The concept is always the same. There's either something in this thing or there's not something in this thing. And so you end up with an algebraic data type of the abstract type on the top and then these two subtypes underneath it with the two different states in it. List is actually very similar to that. So any given list can either be empty, in other words, it's like a nil, or it can be an item followed by another list. That's the beauty of linked lists, is they're very, very simple in this kind of concept. The next list, the tail of that list, could also be nil, in which case you've got a list of one item. Or it could be itself a non-empty list, and that can go on for any length. So that's how you build up a list. But there's only two subtypes of dead simple list, and we've got them here. So the first one is dead simple list nil of type T. That extends that. And now we can look at these implementations of these functions that we defined, that we have to supply. So map for an empty list is very simple. It just returns another empty list of that type. So that's what, oh, I'm pointing to it, but not with the green thing. That's what this guy here is doing. It's taking the function that we pass in. It doesn't really matter what that function is. It's not going to use it in this case, but it has to be there to satisfy the type signature. All it does is just returns another empty list in this situation. And then another thing about algebraic data types is they usually end up being incredibly simple in their implementation. So is empty for nil is always true. That's all you need to fill in for that. And the contents as a string are always nil. That keeps it nice and simple to use. The not quite as simple case is the case where we've actually got something in the list. So here is a non-empty list. This is a list item that has an item in it and then is followed by a list. And traditionally in functional programming, these things are called cons, as in kind of list constructors. So here is our dead simple list cons of t. And for this, we have our item. That's the head of the list, right here, private t of head. And then we have the tail, which itself is another kind of list of that type. It can either be empty or it can have something in it. Because we actually have something in this, we need a constructor. So we create a dead simple list constructor, t item, and then the tail of it. The map now has to actually do something with that function that we pass in. So what it does is returns a new dead simple list construction of the result of applying the function to the head, in other words, the item in us, and then mapping basically recursively calling the map function on the tail. So what this will do is just go along the list and call that function, that same function, recursively across the length of the list. And then the rest of the algebraic data type, very simple, is empty is always going to be false for a constructed or a cons list because it has something in it. So that's the false there. And to print out the string, what we do is we take the item that's at the head of this, we do a toString on it, we add this colon colon, again, is just a functional programming default or style. It just means cons, colon colon, and then we get the rest of the tail, the rest of the list as a string. Okay, so hopefully that covers that. So what you get out of this is that list, the list that we've written, is a functor. It has that that map defined. I'm getting ahead of myself. It has that map defined, and we can see it working here. This is just some support code. You can go back and look at it later. This is largely uninteresting. It just sets up one of these lists and lets you run things on it. And down here we can see it in use. So here's an example. All this code does actually execute. I wrote it in using the Java 8 the Java 8 JDK and compiled and ran it. I wouldn't recommend using it in production, but it works nicely for demonstration purposes. So here's an example. We can take the numbers from 1 to 10 and print the contents out as a string. We can map a function to square those. Oh, I should be showing this. We can map a function to square those, where x, and for those of you who haven't seen Java 8 lambdas yet, this is how they look. That function that we said, we've got a function from int to something, or from t to u. In this case, it's an int to an int, and we can write that. And all a lambda is an anonymous function that's written in a very streamlined way. It doesn't need a name. All it needs is the incoming value, the incoming parameter, and then this kind of rocket, this arrow that defines the lambda, says this is a lambda, and then the result, these two items multiplied together, is the result of running that. And so you can see we get a new list out here, and we can print that out. And then the third one here is something that's quite nice. It's been in there since Java 7, is using a method reference. So our number of stars, which was on the previous screen here, this guy is a function from integer to string. It takes an integer, gives back a string. And so when we apply that, we see what we get back is a dead simple list of strings now. So this shows that the outer container stays the same, but the type inside of it differs. and we can print that out and we get back the list of stars. Okay, so that's a functor. Okay, and functors are not just about lists or collections. This code is actually taken from the Java 8 libraries directly. The only thing I did was remove the wildcards because they just make it noisy and difficult to read the code. But this is the optional type that I mentioned, and you can sort of think as optional as a collection of at most one thing. That's a good abstraction to start with. As you start digging into functional programming more, you'll want to let go of holding on to concepts like that too tightly. But it's a good starting point. So this is taken from the Java 8 libraries, and you have the optional T. And then down here you have the map defined, okay? And this makes it a functor because it is a map operation that has the correct type signature for dealing with mapping something over the contents of that optional type. You'll also find a second function in here. Now let's take a look at these type signatures first of all. So the map type signature is the one that we've seen so far. It takes a function from T to U, and it gives you back the same type, an optional of U. Okay, that doesn't matter what this thing's actually called. In some other, it's usually called something like map, but different languages call it different things. The type signature is what really matters about this. It takes in a function from T to U, and it returns you this same type, the same outer type, but of U instead of T. But there's also the second thing defined in there called flatMap. And if you look at this guy, it's very similar to map. The difference is that the function it takes goes from T to an optional of U. In other words, instead of just going from T to U, it goes from T to another type, the same as us, containing U. But the resulting type is still an optional of U. And so what you can think of this, it's called flatMap in some languages. It has different names in different language libraries. Haskell calls it bind, for example. But the idea is that it applies the function just like we did for the map function. But after you've applied that, what you'll actually end up with is an optional of U. And then the flattened part takes out one of those levels in terms of the types. Why this matters? Well, we're about to see that. So, what is this flatMap? Well, flatMap is one of those things, just like with a monoid, where you have the combiner, the zero value or the starting value in the combiner. Flatmap is an essential part of what makes a monad. Okay, it's one of those things. It's one of those technical requirements that you have. And very roughly, it depends on the type that you're going from. It depends on the outer type what the operation implementation actually is. It's easiest to think about in terms of things like lists and options because those are easy concepts to grasp. But basically, what you get is a fairly simple set of state transitions. If you start with an empty box, I should be the green thing again. This is starting with a none or an empty optional. And the result of mapping or flat mapping any function over an empty gives you an empty. That's very simple. If you start with contents and the function that you run produces an empty or a none, then the result is an empty or none. And if you start with contents and you run the function and it gives you back, that function actually gives you back an option of B, some contents of B, then the results are a contents of B. So it really is it's running this function based on these rules, and it will always give you back the same outer type with single contents in it or none in this case, or empty. That type signature is what really matters for flatMap, and it's very simple to understand for things like optional, but it applies, and we'll see this, it applies to things like futures and all these kind of clever concepts that allow you to do really neat stuff. It lets you basically feed forward values into a workflow where all of the rules are defined. Starting from this, you end up with this other state. and you can, iteratively, just like with a monoid, where you just kind of consistently and repeatedly apply this thing, you can do the same with a monad and kind of work your values through the system. Okay, so I think I better pick up the pace a bit here. Other flatMap implementers. So far we've looked at lists and options, but there are a lot of different implementations of monads. There's lists and collections, which we've seen already. Now, in Java 8, there's the new Streams API, which is actually phenomenally good. I haven't programmed in Java for quite some time, and putting this talk together, I went back into Java 8 and, in particular, looked at Lambdas and Java 8 Streams API, and they're both really well done. They're very clear. They're very familiar to people coming from a Java background, but they still have all of these, requirements met to be, full functors and monads. They've been very well handled. Futures is another thing, and we'll see some demos of that at the end. Futures are great because these are all things that haven't happened yet, but you can still do operations, or I should say may not have happened yet. You can still do these operations on them and keep them as a future thing. So you're basically banking up work to do when the results come in, but not waiting for them at any point. And this is really the core of this kind of concept of reactive programming, if you've heard of that. The reactive kind of movement or manifesto where nothing waits for anything. All of these things are possibly going to happen in the future, and when they do, here's what you do with them. Scala also has a try operation, or a try monad, which is actually, depending on who you talk to, not strictly speaking a monad, but there's some debate around that. But basically what that is wrapping try-catch operations, and instead of actually having them throw exceptions that interrupt the workflow of your program, they just store the fact that something failed at this point. And then, just like option, where if you've got an empty, it feeds forward an empty, with try, if you've got a failure, it feeds that failure forwards rather than continuing to work on it. And of course, when you get good at these things, and if you're ambitious, you can actually roll your own things. My dog has just decided to start dreaming, which is a lot flirting. Anyway, so you can also roll your own monads. Okay, so I mentioned with monoids, there are some laws that need to be met, and these are true for functors and monoids as well. I'm not going to spend a lot of time on them, but the examples in the code in particular are here. Functors, in order to be a functor, as well as having a map function, you also need to have the rules that if you map the ID, if you map a function that takes the thing and returns that thing, if you map that over the functor, you should get back the functor exactly the same, with the same contents. And then composition, if you map A and then B, these two functions composed, that should be the same as mapping A onto X and then mapping B onto the result of that. If you satisfy those, you have a true functor. Okay. I guess, yes. Question here. Who has used Java 8 streaming API in either production or just messed around with them? Oh, okay. Overwhelmingly, it seems... I'll let it go for a second here. I think that's probably enough. Okay, so pretty overwhelmingly, people haven't used streams yet. And I would say this is, if you want to go on to the next kind of learning experience about monads, Streams API is definitely worth a look. It's a really well-written API. Everything is done lazily, so everything is sort of composed as functions and done when you actually run the entire stream end to end. The source is available to you. You can, if you want to, single-step debug through it and look at what it does. It's a great way of seeing how a real non-trivial system is written using functors and monads and that sort of thing. Okay, the monad laws. These are the same kind of things for monads that you get for monoids and functors. These take a lot of kind of grokking, of contemplating to understand, but again, I've written out some code which hopefully will help you sort of get to the bottom of them, at least in terms of option. These are actually written in Scala code, but in the form of options, or option in Scala, some means there's something in it and none means there's nothing. And these kind of demonstrate these left identity, right identity, and associativity rules that you have to satisfy in order to be a true monad. Okay, so Java 8 Streams example. This is an example of this Streams API in Java 8. And it's very simple to use. You create any kind of collection. List is usually a good starting point. So here's creation of a Java 8 list, or just actually a Java list. These have been in Java for quite some time. When you want to use it as a stream, you just say list.stream, and then you can say filter. Okay, first of all, filter we haven't really covered yet, but it's pretty clear what it does. Anything. This is inside of here is a lambda. And in particular, there's various names that functions are given, or lambdas given, depending on what they're used for. And when you have a lambda or a function that goes from an item to a Boolean, either true or false, that has a special name called a predicate. And a predicate is just true or false for any given input value. And so here what we can do is say, given x, it's true if x mod 2 equals 0. So we're looking for the even numbers here. So that just takes out all of the odd numbers. It doesn't pass them forward through the rest of the stream. Then we see our map here, and this map is what that we're using this as a functor. So this map function takes x and squares the result, but it will only do it for even numbers because we filtered out all of the odd numbers by this point. And then this reduce operation, you'll see, should be a familiar concept by now. It has a starting value and it has a function to combine things. So inside of here, what the reduce takes is actually a monoid. It's the starting value and then the combiner. And you see the kind of idea that these concepts are applicable. They're very general concepts, but they're applicable in all of these different kind of situations. Likewise, down here, there's an all by all sum, and this guy is this is using flatMap. So what this is doing is taking the list and streaming it, and then for each of the items in that list, it does another stream over the list, and it flatmaps those together. Okay, it takes the outer number and multiplies it by the inner number of each stream. But the result of that function isn't another integer, it's a list stream of integers. So we have to use flatMap around it to pull out that one level of indirection. So this is just an example of how flatMap can be used. And the result of doing this is just the sum of all of multiples of 10 and 1 to 10, all combined together. Not sure quite why that's useful, but it's a nice little example of how you can use flatMap on these things. And it demonstrates that lists or streams are both functors and monads because they have the map and the flat map. I haven't talked about one other thing, which for completeness I should. As well as a flat map, monads need to have something called an apply or a point or a return. The name varies, but basically what that does is allows you to take any item and wrap it in that monad. And that's an essential part of the type signature. Okay, so Java 8 optional, like we saw before, this is the optional value in Java 8, and it can either have a value in it or not. And here's some examples of those being used. The optional result can be flat mapped over, and you can do things like doubler up here. It's an optional of type of 2, so it's got something in it, and that value is 2. And what it means is that you can take the optional result, which could be none or could be some, and you can take the optional multiplier, which could be none or in this case could be 2, and you can multiply them together and you get back an optional integer. And the beauty of this is if either of those values is none, it can be, if both of those values are there, it will do the multiplication, it will give you back the optional value, the optional result. If either or both of them are none, you will get back an empty result. You'll get back a none result. And all of this is done without ever having to worry about things like null checks. So, the alternative in Java traditionally is if something's not there, you stick a null in there. And then you end up peppering your code with all these null checks all over the place to make sure that you haven't violated some assumption about something being there or not. And the beauty of putting these things into the type system, as you work with these, you'll really see that, is that right there in the compiler knows that something may or may not be there. It doesn't have to worry about null checks anymore because you're actually saying, well, you can't just access this thing. It's inside of an optional type. You have to acknowledge the fact that it may or may not be there. And then you get these operations like map and flatMap that know how to deal with the situation of something missing or something being there. Okay, now I'm going to put a little bit of a sting in the tail. So all of the examples so far have been into Java 8, and Java 8 has integrated functors and monads into the API and provided these optional types and streams, and they've done a really good job of it. There is, however, something that other functional languages have that Java 8 still doesn't have, and I don't know whether they will at some point embrace it or not. But other functional languages actually, because this concept is so universal and so widely used, they actually give you some keywords, some syntax in the language that makes it a little bit smoother to use. So we're going to have a look at the same sort of code that we were just looking at, but using Scala. And this is exactly, you'll see if I just go back a couple of slides to the streams one, you'll notice that to this point, this code looks remarkably similar to this code. There's very little difference other than the fact that the lambdas, or the function literal operators, are now equals greater than instead of minus greater than. Otherwise this is just another lambda. But we take the numbers that we've got in our list and we filter them. Again, make them even, just the even ones. We map the function to square them, and then instead of a reduce, there's just a name change here. There's this thing called fold left, and it does the same as the reduce. This again is the monoid. It's got a starting value and a combiner. And then the same here. We can do the nums, and we can do flatMap again. FlatMap over the outside and a map over the inside, and the result is that we get the list of, we get the result of all of the numbers multiplied by all of the numbers and then summed up at the end of it. Now that's, basically a direct translation of what we saw in Java, but Scala also has, and this is Scala's option, again, very similar to the Java 8 option. You can see, for example, here, double all by all, and we can flat map the first number over the second number and multiply them together, and we either get sum or none back based on the input values, so it's all safe. But this is where it gets interesting. So functional languages often have some kind of syntactic sugar for doing these operations because they're so common in a nicer way. And Scala has this thing called a for expression, or a for comprehension. And people coming into Scala for the first time see for and assume that it's about looping. And it can be used for looping, but it's not about looping. What it actually does, the for expression takes the code inside of it and turns it into, following just very simple rules, turns it into chained maps and flat maps. It rewrites the code to exactly what we saw a minute ago. It just makes it easier to write. So it's really there to pretty up these chained expressions, and instead of saying .flatmap, 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 which you end up getting very long chained expressions if you use this a lot, you end up with a nice kind of easy-to-read comprehension that gets turned into all those flat maps behind the scenes. And as you start getting into Scala, you start to realize that for actually has nothing to do with loops at all. It can be used to iterate or to move over things. But the reason it's doing that is because those things are themselves functors and monads. And it's just applying the same rules. And once you realize that, you can put things into for expressions or for comprehensions that have nothing to do with collections anymore. And we'll see some examples of that. So those two and if I go back a couple, those two examples that I just had of these guys, the squares of all the even numbers up until 10, and then the results of all the products, adding all the products of 1 to 10 times 1 to 10 together, can be written in a for comprehension like this. The first one, it still takes the numbers. It takes n from numbers if it's an even number, and then it yields n times n, and then it does a dot sum on them. Dot sum is just a nice little convenient method that's provided on Scala collections for you. And this, behind the scenes, turns into a map. It actually says nums map, and it does the filter. It does nums.filter, n mod 2 equals 0, dot map, n times n, and then the reduce, the dot sum on it. Similarly, this guy, the for n1 from nums and n2 from nums, this guy turns it into a flat map followed by a map. And the rules are just very simple. These from operations here, the left-facing arrow, all of them except the last one turn into flat maps, and the last one turns into a map. And it just follows those rules and rewrites them into flat map and map all the way down. But the result is quite a bit more readable. You can just see that, for n1 from these numbers and n2 from these numbers, yield n1 times n2, and pretty obviously you're getting the product of all of these things multiplied together, and then sum them up at the end. Okay, similarly options, the same thing that I was showing for lists. We can do the same thing for option because it's a monad, and we can say for n1 from optional result and n2 from double A yield the result of n1 times n2. If either of these come out as none, because of the rules of rewriting this to map and flat map, the result comes out as none, and the result is still an option. So this is, just syntactic sugar, but very effective syntactic sugar. Haskell has a similar thing called do, and like I said, many functional languages actually have something to sort of provide this extra level of ease of using them. Now we get on to the really interesting stuff. So I mentioned before that it's more than just collections and options, and futures is actually one of the more interesting uses of these things. So here's an example of a for expression or a for comprehension used over futures. If we have a trading system and we get a quote in US dollars and a quote in Swiss francs, and we want to make a buy based on a particular condition, in this case, is profitable. These things are futures. It could be going off to some web service out on the web that takes 5 minutes to return a result or something like that. And we don't want to block in our program. We don't want to wait for those results to come in. So we turn them into a future. We say eventually there's going to be a value here for these two things. And when we get those values, then we can get the result. The important thing to notice, and I'll demo this at the end, is that because of the rules of this for comprehension gets turned into maps and flat maps. Each of those operations returns a future. So at no point does this block or wait for the results to come in. What it does is composes these things together and returns a future, so it doesn't make anything wait anywhere. Now, obviously, at some point, in order to do this thing, you have to have a trigger or an async call on or a wait or something like that. But the point is you don't block until it's absolutely necessary, and in a lot of cases you don't need to block at all. You can just line up this work to do based on, I've got a future and another future, and the result will be a future. You combine them in these ways, but don't wait to do it. Just give me back a function that does all this stuff. Okay. Try, I'm not going to spend a lot of time because I am running short of time and I want time for questions, but try is a similar thing. You can, using the try construct, you can have things that might fail, and if any of them fail, it carries the failure forwards. But assuming the success, you can again combine these things into a result that gives you what you want. So yeah, just take a look at this code, and have a mess around with try. There isn't a try in Java 8 yet, to my knowledge, but it is useful enough that I suspect at some point it will get written. It's been very, very useful Scala. Okay, so a very quick demonstration to show that this is not all just theory, but actually is is useful in practice. I am about to share my screen. Hopefully this will work. So down here, I have, this is one of the examples that comes with TypeSafe Activator, which is a sort of combination quick start and learning tool in Scala. And this is an example called reactive stocks, which is all about reactive programming and not waiting for anything. There's no blocking calls in this. It works entirely in terms of futures, which are monads. And so the whole thing is set up so that you never wait for any of these things to happen. Everything happens asynchronously, and it makes very, very efficient use of the threads and the available cores and all that sort of thing in your program. And in particular, you'll notice this. Hopefully, this is highlighting. This code here is pretty much exactly what we've just seen. So this is for a particular symbol. We are getting future stock sentiments. Not actually sure what a stock sentiment is because I'm not an accountant or trader, but I assume this is something to do with the stock price. And what we want to do is get a bunch of tweets for that symbol. So this is what this first line is doing, and this returns a future. Okay, you'll see that the overall result of this is a future. This guy returns a future. This guy the second line also returns a future based on each of the tweets. In fact, this is a sequence of futures that will give us back, based on all the tweets that we get back a sequence of tweets for that. And so this is flat mapping the result of get tweets into this guy, and this guy is then going to produce a sequence of those futures. And then finally, there's a very useful library utility or library function in most of these future implementations called sequence. And what that does is it takes any sequence of futures and turns them into a future of sequence. So it sort of flips those containers around. So it means that you get a single future back of all of the contents. It's very cleverly implemented, and if you're interested, go and have a look at the implementation to see how it does it. But it means you can take a bunch of futures and turn them into a single future with the result of all of those things in it. And then eventually we yield, and this is play, this is the play framework, so we're yielding an OK page based on the future of those sentiments. And the amazing thing about all this is it's very clear to read, it's very clear to see what's going on, but nowhere in here does this loop block. It runs, or it returns immediately, and what it's done is just composed a bunch of these functions together, and when the results actually come in, it will run them. But at no point does it block. It's all working in the future. And the result of this gets turned into a page. That page is also a future. We actually get a future of result back, which is what this is saying up here for the page. And then because play has been written this way, you'll see the action actually has a .async on it. And so what that means is it's not even expecting a page back. It's expecting a future of a page. So nowhere in this does it block. As soon as you call get, it returns pretty much immediately, but it's all this work that will be done. And then the framework actually handles sending that back out to the client when it's ready. And so all of our code never blocks. It just makes the most efficient use of the available resources all the way through. Okay, I think that's probably me talking for long enough. So let's go to, I think, Q&A. Yep, I should be back to the slides. So let me see what the questions are. Okay, so the first one is, are streams tail recursive safe? In a sense, can you get a Stack Overflow when mapping over them? This is from Alexander. Alexander, I don't know the answer to that because I haven't looked at the implementation of the API. But knowing the people involved, I'd be very surprised if they hadn't made it safe. I expect one of the little secrets that you actually learn about when you start doing this stuff, the type signature, satisfying the type signature is key. Making sure that it behaves itself and adheres to the type signature is what matters. Behind the scenes, the implementation is often driven by what's most performance rather than what's functionally correct. The result will be functional safe, but quite often you'll actually see things like loops used and while loops and things like that, because they're very much more performant than the recursive approach. Scala has a trick that it takes tail recursive calls and flattens them out into while loops behind the scenes. Java doesn't have that. So I would imagine that the Streams API, and I would need to go and check this, but I would imagine that the Streams API in Java actually uses loops and things that are safe with the stack, so it doesn't blow the stack. Going back to is every monad a monoid? Yes, it kind of is. There's actually a famous quote by a good friend of mine. He said it jokingly, just to kind of perpetuate or continue the myth of these ridiculous names and concepts that everybody throws around for these fairly simple ideas. And he said, a monad is simply a monoid in the category of endofunctors, which is absolutely correct and utterly incomprehensible to almost anybody who's read it until you sit down and think about it for like an hour. And then you realize that it is actually utterly correct. But basically, a true monad satisfies the same rules as a monoid. It has to, because of all of those things like applicative, the order that things happen in. And the whole endofunctors bit just means that what you start with is what you need to end up in terms of the type, the type. So if you start with a list, you end with a list. If you start with an option, you end with an option. If you start with a future, you end with a future. So yes, technically speaking, monads are monoids for that particular case. They have a combiner defined, which is the flatMap, and they kind of feed it forward. The next one, Terry Lynn says, how about applicative? Could you briefly explain? Yes, it will have to be brief. I did think about putting applicatives in here, but it is one more concept. So applicatives are a more general, also called applicative functors. They're a more general kind of case of the same kind of concepts as monads. And really, I think the best way to describe them briefly is applicative functors are functors with a couple of extra requirements, like those Functor Laws. They're beefed up a bit in terms of applicatives. And basically what they say is, for functors, you've got that if you map the ID, you end up with the same thing, and I forget what the second one was offhand. I'll have to go back and look, but it's those two rules. For applicatives, you actually have the requirement that these things have to be fully associative. They have to be able to be applied in any order, starting with the items applied in the same order, but the evaluation can be done in any order, and the result has to be the same. And when you get that, you end up being able to basically parallelize these things with applicatives and do all these kind of clever combination tricks on them. It sounds like some of you are actually really interested in this, taking this further, which I hope is the case, which is a good time to plug my friend Runar's book. Runar Bjarnason and Paul Chiusano have a book called Functional Programming in Scala, and it's probably the clearest explanation of these kind of concepts that I've seen. They're both very good authors. So if you are interested in it covers all applicatives and has you write all of these things down, like starting with monoids and functors and monads and applicatives, and it has you write them as exercises during the book. So if you make it to the end of the book, you will really get this stuff. Okay, next question. Unlike Scala, in Java 8, the collections are not monadic. You need to use a stream to... Yes, that is correct. So this is Sam DeBacker, and he says, unlike in Scala, Java 8, the collections are not monadic. You need to use the stream to obtain a monadic collection. That's correct, except the stream really isn't, and that's really what's clever about this. Streams are not collections at all. They're lazily evaluated monads. So you actually go into this space where when you're applying these functions, the work isn't done immediately. I mentioned earlier the type signature is king, and the implementation is up to the implementer. And in the case of streams, that implementation is sort of storing the functions to work, to do on these streams, but not actually applying them until the result is forced in some way. And that has all sorts of advantages. Let's say you have a heavy operation that you're doing, that you're mapping or flat mapping across one of these streams, but you only take the first 100 items, or you only take every third item. It means that the work doesn't have to be done for the rest of the items that you're not taking. And that's very clever. So it only applies the functions when it absolutely needs to. And that's a really nice feature of kind of streams and lazy evaluation, is you can choose the manner in which you satisfy the type signatures that you've kind of signed up to take on. Okay, next one. List is mutable, but list.stream produces an immutable stream. I think it's not. Yeah, it is. Yeah, all of these things are immutable in terms of the stream. Every time you perform an operation, you get a new stream back that has the new information on it. The result, when you actually want to get the results, you have to force it in some way. So you have to assign it to another list or something like that. Whatever you assign it to is going to end up conforming to that type. So if you assign it back to a list at the end of it, you're still going to end up with a mutable list. But while it's in that stream space of lazy evaluation and applying these things when they're forced, all of that is monadic and as a result is immutable. Every time you do an operation on a stream, you actually get a new stream back with all of the old stuff in it plus the new bit that you just added to it. Is a functor the transformer of a structure that allows transformation? This is from Sam DeBacker, and I need to parse this question to understand it. Is a functor the transformer of a structure that allows transformation? The functor, all of these concepts are sort of tangled up together. So a functor is sort of a combination of the container that, some kind of container, some kind of thing that holds these values or encapsulates these values, and the nature of what they can do with them. So you can think of functors as, something that holds onto things and also allows that function to be mapped over them. And this is why it's very difficult to explain these concepts, because it's not just a single chunk of code that makes it a functor. It's this combination of the implementation, the functionality it allows, and then the third aspect is these laws that you have to kind of satisfy in order to actually be a full, a proper functor or whatever. So I'm understanding that monoids are operations that are reflexive, symmetric, transitive, and with an identity element, and associative, but not commutative. That is correct. The last one is it doesn't have to be commutative, and the example there is string concatenation. So commutative is where you swap the values order. A plus B equals B plus A. You don't have to have that to be a monoid. And the reason is, if you did string concatenation, if you had hello and world, and you concatenate hello world, that's not the same as concatenating world hello together. So yes, commutative is not a requirement for monoids. Basically, what's a monad? I'm not sure you're talking enlighten me. Sorry, Pierre. It is difficult to explain. It's called the curse of the monads. I had hoped that this would at least reach a broader audience because of the Java 8 examples, but it does take a while to get these concepts. And all I can say is maybe go back and listen or watch again. Have a look in the book, and if you're motivated, just keep plugging away at it, and you will gain enlightenment, I promise. Oleg says, why are monads so important? I understand that all examples shown are instances of a monad, but why do we need the monad as a type class? Oleg, the answer is you don't need the monad as a type class, but it can help you organize your thinking if you have it. Scala itself doesn't have a monad class defined or a monad abstract defined. It simply has the 4 expressions that you can use, and if you know that flatMap's on something, you can call it. Scala Z, which is a library, a very functional library for Scala, does formalize things into monoids and functors and monads, and that's really to help that's to help 2 things. It's to help the thinking and the organization of the libraries, and it's also to allow a level of generic programming that wouldn't be possible otherwise, because you can say this thing is a monad. Now you know that it's always got a flatMap method on it. So you can say, I'll take any monad. It doesn't matter what it is. I know that I can call flatMap starting with this value and end up with this value. So I hope that answers your question, but you don't need to have these things as type classes. Some libraries do it because it makes it easier to program generically with them. Laura, how am I doing for time? Can I keep going on the questions?
If people need to hop off, if they have a time constraint, then they can do so. And Dick, if you want to finish up with the Q&A, that's fine. The talk is recorded, so if people are needing to dip off, we can just share the end of the Q&A with them.
Okay.
So why don't you take up more that you think are relevant, Dick, and then we can wrap up.
Okay, yeah, there's only a few left, so I'll just keep going. And
Great.
If I've lost people, sorry I talked too long. So, okay, so the next one, Christopher Ambler. Oh, hang on. Mike Bobrov says, if Java has all these functional things, will it kill Scala? That's a question I get asked a lot. I think it's great. I can't imagine a better outcome for Java than having functional programming enabled by lambdas. It's a huge step forward. I think that actually, my opinion is that it ends up being sort of a gateway into a larger world of functional programming. And I think that, for a lot of people, Java 8 will be everything they need. It certainly is a huge leap forward in the functionality, and it enables all sorts of new libraries and approaches. But I think there will always be a percentage of people that look at that and go, wow, what else can I do? And, for that, languages like Scala and Haskell and Clojure are right there waiting to kind of receive you with open arms and say, well, if you really want to go functional, here's what you can do. And it certainly doesn't hurt. I've said for a long time, learning another language, whether you intend to use it or not, is a great way to improve your skills in your current language. You get introduced to all sorts of new concepts, and then you can bring them back and kind of fold them in. Certainly people who used Scala over the past 5 years see the lambdas and the streams API in Java and are immediately familiar with them. I was amazed how easy it was to use them after 5 years of not using Java at all, because all the concepts were so familiar. So I highly recommend that as sort of a learning experience. Christopher Ambler says, do Java 8 optional and Scala optional play nicely together? That is, can I have a Java method return an optional and some Scala code consume it without any fancy translation code? Christopher, at the moment, you can apparently do it using a feature in Scala called implicits, which will do that. It will basically do that fancy translation, but hide it from you so you don't have to see it. And that will work both ways. Scala 2.12, the focus of that is bringing in kind of much greater or tighter compatibility with Java 8. So I expect that situation to get a lot better without needing implicits in the Scala 2.12 timeframe, which is not that far away. So, this is from Sang Venkatraman. A simple question, isn't string concatenation not dependent on the order? Yes, this is going back to the commutative thing that I answered before. But very briefly, it does matter the ordering that whether A plus B or B plus A is observed. But what the associativity means is that A plus B plus C should return the same result as A plus B plus C, with the pause being the order that those happen. So that answers that. You have to have A, B, and C concatenated in the same order of the items, but the evaluation order of those must produce the same results. Can you explain the relation between and then and on complete? I assume this is, well, actually, these concepts are kind of universal across Java 8 and Scala. So and then takes two functions together and composes them. So if you've got x times 2 and x plus 3, the result will be a function of calling and then will be a composition of x times 2 plus 3, okay, when you do and then. And onComplete is something that you use for futures, and what that says is, here is some code that I want you to run asynchronously once the future has actually resolved, once we have an answer. And that onComplete then fires. So this is like your event handler or your callback. None of it's blocking. It all just queues up code again to run when ready. But that onComplete gives you something that you run when everything's resolved. Michael Anas. Oh gosh, some of these names are really hard, you guys. Mikhail Anastopoulos. Sorry, Mikhail, I just butchered your name. How do futures map to threads? That's a great question. It's kind of one of those how long is a piece of string questions. It depends on the implementation. Futures and actors in particular generally work with thread pools, and because they're non-blocking, because they don't have any kind of await states, or they shouldn't have any awaits or thread sleeps in them, they actually never block, and they can be swapped in and out of a thread pool to efficiently use it. And the reason you want to do that is threads are relatively heavy, particularly on the JVM. You can have, I think, you can have maybe 1,000 of them before things start to really bog down. But if you get too high, you very quickly end up in this kind of horrible place of thread swapping and all these overheads of trying to manage these threads. But with actors, you can have millions of actors, depending on kind of the memory resources. And what they do is they all share these thread pools, and they get swapped in and out and stuff like that. And futures, similarly, can sort of hop into a thread inside the thread pool and work on it, and then relinquish it for other futures to use. It does depend on what the implementer has implemented it as, though. So it could be that a future is mapped directly to a thread. That would just be a very inefficient way of doing it. As M. Khan says, flatMap is the equivalent of bind in Haskell. What's the equivalent of Haskell return? Yep, that's exactly right. flatMap, bind is just what flatMap is called in Haskell. And Haskell's return is, in Scala, typically that's implemented as an apply. It takes the item and wraps it in the monad and gives you back that monad. And apply is just, it's the factory method for constructing these things. So typically that's what it's called. In Scala Z, they have a different name for it, which you'll see called point, which just makes things a little bit more confusing sometimes. But yeah, all of these things are just names that they all have the same concept of taking this thing, wrapping it into one of those monads. Gabrielle says, is there a pattern to provide a notion of transaction on cascading futures? If you fail one, you would like... Oh, yes. Okay, Gabrielle. So this is not really... What Gabrielle is asking, I believe, is about recovery of failures on futures. And this is not something that's necessarily monadic in nature, but it is implemented on pretty much every future that I've seen. They have these kind of recover and recover with methods, which take functions themselves. And the idea with them is, if there's a failure along the way, this is code to execute to try and recover it before you give up as a total loss. So the futures are usually implemented as some kind of, because you can have failures, because things can go wrong in a future. When things do go wrong, you kind of feed that failure forwards. And if you have a recover in there, then if the failure hits that, it actually tries to correct the situation. Maybe it goes and retries a few times. If it's like a web service, you say recover or recover with, and go out and hit that thing again 5 times, hoping that one of them will work. And eventually you kind of give up and say, okay, it's really down. I can't do that. So yeah, there's recovery options like recover with and stuff like that on them. And then the last question is, so if the underlying list changes, the stream changes. This is from Brandon Hudgens. Brandon, I don't know the answer to that without looking at the code. It's possible that, so the idea is that the stream is based on the list, and the list is mutable. So if the values in the list change when you're processing the stream, the result of doing that changes. I don't know what the implementation is. They may have taken a defensive copy, which would be nice but would be slow. Remember that the stream itself doesn't actually do the work until you force it. So the answer may be that they implemented it so that when you actually process the stream, that's when the resulting, calculation is done, and whatever is in the list at that time is what gives out. It'll be an interesting experiment to run. But yeah, without looking at the code, I don't know. This is one of the reasons why functional programming languages tend to emphasize immutability, because it makes stuff like this a lot easier to reason about. If you know things aren't going to change underneath you, it's a lot easier to know what the result could be. So yeah, that's just something that's kind of unique to Java. In Scala, most of the collections are immutable by default. You have to actually work at getting a mutable one, and it's for reasons like this. Okay, I think that cleared all the questions, so I think we're about done. Hopefully that
I think you got it.
That was useful. I think there's going to be some feedback at the end. I know that at least one person still doesn't understand them, so I'm sorry about that. It is a difficult concept, but like I said, the thing is to keep plugging away, and the important thing is to know that if you're using Streams API and Option and Futures, you're kind of using these concepts and getting the advantage of Monads, whether you understand them or not. It's really to sort of demystify the whole thing is the reason for this talk, to sort of say, they are very nebulous, they're very hard to pin down, but the concepts are not that difficult. And if you just realize that they're very general and that they apply differently in different cases, it makes the whole thing seem a lot less magic than it did before. So, okay, I think that probably wraps it up. All right, thank you.
I think so. Yep, thank you, Dick. That was wonderful. Thanks for taking the time to address everyone's questions. And for those of you who tuned in, we will be publishing the recording shortly, so look for that. If you registered, you'll receive a direct link. And if you have any questions, just feel free to reach out to us. So thank you. I hope everyone has a good rest of their day.
Thank you. Bye, everybody.